Hello. In this video we're going to be exploring the inclining experiment. So the inclining experiment is typically done to determine the kg of the vessel. It can be done for the lightship of a vessel. Typically it's done for the lightship after a new build or after some kind of modification in a maintenance or yard period. The basic idea here is that you have a known weight. You might load it up on the center line. And on the ship you will hang a pendulum. And you'll know exactly how long that pendulum is. And down at the bottom of the ship you're going to set up, a kind of a wooden batten down there. And that pendulum will have a plumb weight on it. And then what you'll do is you'll take that weight. You'll know what the weight is, and you'll slide it a known distance to port or starboard. In this case, if you're looking at it from astern, the weight was, they slid the weight a known distance, from center line to starboard. And what happens then is that pendulum is deflected. It's deflected a certain distance, and you can actually measure it on the batten. You can draw a line there. So you have a line drawn for the center line. And then you have a line drawn after you've inclined it with a known weight and known distance off the center line. And now you have a deflection. And there's a ratio of the length of that pendulum and the deflection. And that we can relate that to this angle theta, which would be the angle of list created by that off-center weight. So let's look at this a little bit more carefully now. So in this picture here, this is our vessel. We're looking at it from stern. Here's our known weight. We're going to end up sliding it a known distance here to starboard. This line here is our pendulum, and our pendulum is actually lined up on the center line, and here's our batten. So as I slide this weight to starboard, oh, by the way, we know the length of this pendulum. We measure it very carefully before we start this. And we mark where the pendulum is on the batten before we shift the weight. So now we shift the weight to starboard, and in the process of doing that, the pendulum will still be vertical, but since the vessel is inclined, we'll have this deflection here from where it was on the center line before inclination to where it is now after we inclined it. And so we have a ratio of this distance versus this distance, so we can measure those carefully. So batten deflection, length of the pendulum. Well, this angle theta can now be related through the tangent of the theta. So tangent of an angle is opposite over adjacent. So here's our hypotenuse. Here's our opposite. If this is our angle, this is the leg opposite, the side opposite. This is the side adjacent. So we can say that tan theta equals opposite over adjacent. And now we can name that opposite. That opposite is the deflection along the batten, and the adjacent is the length of the pendulum. Okay, so now this is the same image, and what I've done here is just recreating the previous slide. Tan theta is opposite over adjacent, which is deflection over pendulum. So now we can look at this another way. We can look at it from this perspective. I had a vessel, and it originally had a G here. Here's the keel. That's our kg, and the weight was on the center line. As soon as I shifted that weight, from the center line to some known distance to starboard, G will shift as well. And G will shift parallel to the shift of the weight. So you can see that G was here. I moved that weight out there, and that moved the weight off center, which is essentially what caused the vessel to incline. So G went from the center of gravity, shifted from the center of gravity here, G, to the new center of gravity, G prime, and we call that GG. Well, so we can draw that down here too. So we have our metacenter, and we have the original center of gravity, and we have the new center of gravity caused by the shifting of this weight. And so we have GG and we have GM. Well, if tangent theta is opposite over adjacent, we can now define that as tangent theta also equals GG, the shift of G, divided by the GM. And now you can see actually that these two formulas could be set equal to each other. Tangent of theta could be deflection over the pendulum, or tangent theta could be GG over GM. Okay, so now we're going to use these images to derive a new formula for GM. So remember here we had a weight. It was a known weight that we shifted a known distance, okay, from the center line, and that created a list, okay, and that list has an angle theta. And remember, the vessel has a metacenter, and it has this G was where the center of gravity was before we shifted the weight. And after we shifted the weight, the center of gravity shifted to G prime. So this is GG prime, or shift of G. And there's theta. So this from G to M is GM. So we can come up with this formula: tan theta is shift of G over GM. Now, all I have done now is I have just solved, this is formula solved for tan theta, I've just solved it for G. All right, so these are the same formula, just this is now solved for GG. And the reason I did that is because we're already familiar with another form of the formula GG. Weight times distance divided by displacement. Up to this point, we've been using this formula for the vertical center of gravity, but it can also be used for the transverse and the longitudinal. But right now we're just interested in this shift, this transverse, sideways, lateral shift of G. So if GG is GM tan theta and GG is weight times distance divided by displacement, then it makes sense that we could set these two equal to each other. Okay, so that's essentially what I've done. If I said that GG equals GG, I can just substitute these two in there, and now I have this super formula. And now, if I solve this for GM by dividing both sides by tan theta, I come up with a new formula for calculating GM. Okay, if I have a weight that is a known distance shifted from the center line, I divide that by the total displacement. I can measure that angle created by that off-center weight. I can calculate my GM. All right, but remember too that if we think about this in terms of a pendulum, that deflection and that length, well, that is also equal to tan theta. So tan theta could be GG over GM. It could also be deflection over length. So I could also solve this formula. GM could also weight times distance divided by tan theta, or I could just substitute deflection over length in there for as well. And typically this form I'll use when I'm doing the inclining experiment, where I'm trying to calculate the kg of a lightship. And this form I'll use typically when I am trying to figure out the GM after shifting a weight. Okay, so it's the same basic formula for a couple different methods. Now, at the end of the day, we also might want to calculate kg. Remember that the kg is km minus gm. So if I look up my km based on my drafts, I can figure out my kg. So the beauty of this formula is that we can also solve it for a weight, we can solve it for a distance, and we can solve it, we can determine angle. And so this formula here in these two forms, very important. We're going to be using this for multiple calculations, and you're either going to want to memorize, I suggest you memorize this formula and then be able to derive it for all these, but it's up to you what you want to do.